Welcome to the MIME product overview presentation. In this presentation, we will be introducing the MIME mesh generator, highlighting its key features, discussing the guided workflow that is provided by the MIME user interface, and finally, discussing how MIME fits in with Metacomp's comprehensive multiphysics software suite. So let's begin with a brief introduction to the MIME mesh generator. The name MIME is an acronym that stands for Multi-Purpose Intelligent Meshing Environment. It is multi-purpose in that it allows users to quickly create high-quality meshes for a variety of analysis needs. MIME can be used to produce both two-dimensional and three-dimensional unstructured meshes. MIME's meshes are regularly used for the full range of fluid dynamics simulations as well as for conjugate heat transfer and structural dynamics simulations. MIME is intelligent in several ways. First, the MIME user interface, also referred to as iMIME, uses intelligence to create a guided workflow for the user, ensuring that users don't miss any important steps of the meshing process. The MIME user interface can automate portions of the mesh setup, saving the user time and reducing errors. For specific applications, the setup is further automated via wizards, which will be discussed in more detail later. Finally, MIME uses intelligent algorithms to produce a mesh of high quality that will be suitable for use with the full line of Metacomp's analysis software. Overall, the MIME user interface is designed to be quick to learn, easy to use by even novice users, and yet provides experienced users with quick access to advanced meshing controls. Touching again on the multi-purpose nature of MIME, it is regularly used to support a wide variety of analysis types and application areas. This slide touches on some of these analysis types, which include the full speed range of aerodynamic simulations, coupled aeroelastic simulations, as well as reacting flows. MIME is used for various automotive simulations, marine and turbomachinery simulations, and for a variety of industrial processes and commercial product simulations. To test the quality of MIME meshes, they are regularly used as part of Metacomp's ongoing validation efforts and across Metacomp's full range of analysis products. This slide shows a sample of a MIME mesh that was used to validate CFD++ for turbomachinery applications. And in this slide, MIME meshes were created to support CFD++ validation efforts for multi-phase modeling and conjugate heat transfer applications. Now let's take a closer look at some of the important capabilities and features that are provided by MIME. MIME provides a wide variety of features to allow users to create the mesh that is needed for their specific analysis goals. Depending on the physics being simulated, it may be necessary to include prismatic cells, which are also known as boundary layer cells, along viscous walls. It may also be necessary to reduce cell sizes within a volume region to accurately simulate separated flows. Or it may be necessary to enhance the resolution of highly curved regions of the geometry to ensure accurate resolution of drag, heat transfer, and stresses. MIME provides a comprehensive set of controls to address these and other important scenarios. Let's start by taking a closer look at MIME's features for controlling the mesh size. Paramount to the process of generating a mesh is the selection of the mesh cell sizes. It is important for users to select mesh cell sizes that are appropriate to resolve the important physical phenomena of the problem at hand. MIME provides a variety of methods for setting the mesh sizes, including global mesh size controls, region-based mesh size controls, and family-based mesh size controls. Additionally, MIME provides entity-based sizing and point set size controls, wherein a mesh size can be specified for each of the geometric entities that define the model or at specific points within the volume of the model. Volumetric density regions allow users to denote regions of space within a selection of analytic shapes, such as boxes, cylinders, or spheres, wherein the cell size will be limited. Volumetric density regions are useful for many purposes, such as the refinements of wakes and regions with separated flow. With these phenomena, the cell size must be controlled in the volume, away from the surfaces of the geometry. MIME is an unstructured mesh generator, but provides control over the element types that are used to create the mesh. Users can request triangular surface meshes, or they may request quadrilateral dominant surface meshes. Within the 3D volume, users can choose between tetrahedral volumetric cells or hexahedral dominant mixed volumetric cell types. MIME provides a comprehensive collection of controls that allow users to achieve specific objectives with their generated meshes. For example, users can set an overall rate at which cells are allowed to change in size. Curvature-based refinement can be activated to ensure that the mesh automatically resolves the curved features of the geometry. In situations where the geometry represents a periodic domain, then MIME's mesh matching capability can automatically enforce point-to-point mesh matches on the periodic faces. User-defined prism layers controls allow for custom prism layer growth scenarios to resolve bow shocks or specific boundary layer phenomena. And most importantly, features like these are designed to be used together so that users can create the mesh that will support their analyses. MIME is built on a framework of automation to improve user efficiency and to minimize setup errors. The MIME interface enforces a guided workflow that allows the setup process to dynamically adjust to prior steps in the workflow. Additionally, the meshing algorithms enforce automated checks of mesh quality during the mesh generation process. When needed, adjustments to the mesh are also made during the mesh generation process to provide users with high-quality meshes that minimize the need for labor-intensive manual inspections. MIME also includes several wizards that can provide further automation of the setup process. For example, MIME contains a generalized size automation wizard. This wizard automatically provides entity-based sizes to match a user-selected size intent. By specifying all sizes for the user's effort is greatly reduced. MIME also includes two application-specific wizards that not only provide guidance on mesh sizing that is typical for such applications, but also provides initial input files for CFD++. Here are two examples of meshes that were produced by the Generalized Size Automation Wizard in MIME. For both of these cases, the mesh sizes were automatically determined by the Generalized Size Automation Wizard without the need for any user size specifications. The images on the left show a typical mesh that can be obtained for a high-lift aircraft geometry. The images on the right show a typical mesh that can be obtained for an appended ship geometry. The Generalized Size Automation Wizard can significantly reduce the user effort needed to create meshes for complex geometries such as these. The capabilities and automations mentioned in the previous slides are enabled by the MIME interface. This interface is based on Metacomp's Integral Computational Multiphysics, or ICMP, framework, which provides for a consistent look and feel relative to other Metacomp software products. The ICMP framework also provides a guided workflow that will be familiar to users of other Metacomp analysis software packages. The MIME guided workflow is designed to be easy to learn and quick to use. The workflow starts by importing a suitable CAD model and then grouping the geometry into families. These families are then used for controlling mesh parameters and for later use for the specification of boundary conditions. This is followed by the specification of mesh sizes and other meshing parameters. The user then generates a surface mesh to quickly verify mesh sizes and surface resolution. For 3D problems, these steps are then followed by the definition of prism layers and the generation of the volume mesh. The final mesh, whether 2D or 3D, may then be inspected and exported to a format that is compatible with supported analysis packages. Let's take a closer look at each of these steps. MIME can import fully enclosed geometries, which are sometimes referred to as watertight geometries, in ASYS, Parasolid, and STL file formats. When used with Metacomp's Sim++ product, additional common CAD formats such as STEP, IGES, NX, CATIA, or SolidWorks can also be imported. As discussed previously, MIME provides several methods for specifying the element sizes. MIME also provides a comprehensive set of features that allow users to achieve their specific meshing objectives. The MIME user interface enables users to specify their mesh controls with little effort. By building a surface mesh first, users can relatively quickly visualize the results of the chosen mesh size controls and mesh features, allowing for adjustments to be made early in the meshing process. The specification of the prism layers is simple and intuitive. Users can first choose a growth algorithm. With the default algorithm, known as Relative Growth 1, users specify the height of the first layer, a growth rate for each additional layer, and an aspect ratio at which the prism layers will cease to grow. Other growth algorithms are provided that allow users to define prism layers using alternate constraints. Users can also define their own prism layer heights to achieve custom prism layer spacings. The volume mesh is produced next. Users can utilize a variety of automatic and manual inspection tools to verify the mesh quality. However, the MIME user interface has been carefully designed to guide users toward best practices. Additionally, the MIME meshing algorithms are designed to inspect mesh quality and to adjust the mesh as it is generated in order to meet internal quality metrics. The end result is that users need to spend less time inspecting the quality of their MIME meshes. Finally, users will export the MIME mesh into a format that is appropriate for the analysis package of choice. Speaking of analysis packages, MIME is designed to integrate with the full line of Metacomp software. MIME plays a central role in the analysis process. With MIME, users can quickly and reliably produce meshes for their unique analysis needs, all within a package that is easy to learn, familiar to use, and supported by Metacomp's experienced staff. MIME continues to be developed and advanced. Upcoming features of MIME include multi-threaded volume meshing and support for mesh adaptation when used with CFD++. In addition, further improvements to the user interface and the meshing workflow continue to make MIME easier to use and more reliable than ever. When combined with CFD++, MIME can be used to adapt meshes to obtain better solutions for a wide range of simulation types and flow conditions. For example, MIME and CFD++ have been used to adapt meshes for reacting flows, incompressible flows, rotating frame of reference flows, and for compressible flows. Thank you for taking the time to learn about MIME. If you would like to learn even more about MIME, or if you wish to learn about the other products in Metacomp's comprehensive multi-physics software suite, please click on the corresponding link below. Also, please feel free to visit the official Metacomp Technologies website, or you may contact us directly at info@metacomptech.com for additional information.